Okay, welcome back. Now we're looking at the combinatorial relationship that we looked some time back. Let's say given 3 points or 4 points, you are not allowed to shatter more than two data points, right? So the first one is taking 3 points, and we are trying to find the number of dichotomies. And just to remind, this line is a dichotomy, all the positives or the negatives that a point can take, all possibilities. So basically we want a set of these possibilities, which is known as dichotomies, and we don't want any pair of points to be shattered. So essentially x1 and x2 shouldn't have like all possible outcomes of the plus and the minus. So as you can see in x1 and x2, we don't have the two positives. So that option is missing, and so it is not shattered. Similarly, you can see for x2 and x3 and x1 and x3. So the number of dichotomies that were possible for 3 points such that no two are shattered is 4, right? We could come up with these like 4 lines essentially. Similar to that, when we were looking at 4 points, and again, the requirement is that no two points should be shattered. That means not all possibilities should be there for any 2 points, whether it's x1, x2, x1, x3, x1, x4, or like whatever pair you're trying to make essentially. So the maximum number of dichotomies that I can come up with is 1, 2, 3, 4, 5. And you can just go and add another dichotomy again and see that two additional, like any 2 points out of these 4 points will be shattered. So this is the maximum that I can come up with. And you might be thinking, why am I so much interested in this? Because this is the basic building block for the bound that we are looking at. And we shall see that in a minute. And because this quantity is so important, we are going to actually define it. And and this is a combinatorial quantity, of course, and let us introduce that. So I'm going to be consistent with what the textbook says. So I'm going to denote this quantity by B and K, where B and K stands for the maximum number of dichotomies, and let me write it down. The maximum number of dichotomies on n data points, because now we are being more generic, right? On n data points, such that no subset of size k, such that no subset of size k is shattered. Okay, what does that even mean? Right? Let's look at the examples that we looked at earlier, right? So basically here, B, and what is n here? 3 points, right? So I'm going to write 3. And what were the subsets that we were looking at when we wanted them not to be shattered? It was of size 2, right? So size 2, and the number of dichotomies, or the max number of dichotomies that we came up with, is 4 in this case. So this is what we are trying to denote, right? The lines here is what we are trying to get. Similar to that here on the right hand side, B, and then the number of points is 4. The number of points that are not shattered is the pair of points. So that means again 2 equals 5. Now you can tell that these are simply numbers, and in this situation this was 4 and this was 2, but these numbers could take different values. They can take other values as well, right? So before like building on this idea of B n of k, we need to understand how do we get the values of different B n's of k's, and can we, by knowing some basic number, right, for some given n and k, can we build on that? So that's the example that we're going to work with first and then move forward, right? So let's look at this example, and instead what I'm going to do is I'm going to draw this like tabular form where we'll come up with the values of B n of k, because this is going to help us build what we are looking at, right? So let's say k values are here and n values are here, and I'm just like looking at some very simple common values, 1, 2, 3, 4, 5, 6. And why are we doing that? Because if we can come up with a generic sort of relationship between n's and k's and the outcomes, then we can actually generalize it, and that's what we need. Okay, so 1, 2, 3, 4, 5, 6. Okay, let's like stick to these many n's and k's, and then we'll see can we generalize them, right? So The first thing that I'm looking at is B n of 1, like the first column. Can we think about it? What exactly is it? Okay, let me just write down. What do you think is B n of 1, or maybe B 1 of 1? Okay, n means I'll have n points, right? So x1, x2, up to xn, and I'll have dichotomies. So let me have any dichotomy here. Let's say this is the dichotomy I have. And then if I need to have more dichotomies, I can just like keep going on. But here my k is 1, right? This is k. And k tells us the subset of size that should not be shattered. So basically I'm saying no subset of size 1 should be shattered. And if I add another dichotomy here, there has to be, like, if it is another dichotomy, then obviously I have to have at least 1 point different from this one, right? I will have like some difference here, at least like by 1 point, and then maybe the rest stays the same, but I'll have a difference of 1 point. And then if I just added one dichotomy, this is going to shatter this point, and that's a subset of size 1. So I cannot have the second one, right? And so Bn of 1 is going to be 1. So that's good for us because we actually found out the relationship between n and 1. So the first column can be filled, whatever n is, right? This is going to stay as 1. Because as you can see, we cannot have like more than one dichotomy there. Okay, having said that, let's look at, let me look at this one, right? The row. So basically B, maybe begin with this point, right? 1 and 2, easier to understand, right? Okay, so this is saying n is 1. So I'm going to have just like 1 point, let's say x1, right? And B1 of 2, if we look at the definition, is telling us the maximum number of dichotomies on one data point such that no subset of size 2 is shattered. Well, I don't have a subset of size 2, right? And the maximum number of dichotomies that I can have on one point is all the possible dichotomies on one point, which is this, right? Had it been 2 here, right? And x1, x2, right? Let me just quickly do the math here, right? So the maximum, again, there is no subset of size. I'm looking at this relationship, 2 and 3, 3 and 4. So let's focus on that. And then I'm going to look at like 1, 1 and 2, 2 and 3, 3 after this, right? So had it been 2 and 3, right? There is no subset of size 3 when I have only 2 points. And I know that I can come up with 4 values for this, right? Because I know this is like 2 squared. That's the maximum number of dichotomies I can come up with, right? Basic counting principle. So I can generalize this by saying that if I had Bn of n plus 1, right, the maximum number of dichotomies is going to be 2 to the n, right? We verified it with B1 and 2, 2 and 3. So what are those like places where we can fill this up, right? Whenever there is an n and n plus 1, basically what we're looking at here is all these diagonal elements. So let's see, like in the table, wherever there is an n and n plus 1. So here there is an n and n plus 1 because n is 1, right? So this is going to be 2 to the n, right? Which is 2 to the 1, which is 2. Oops, what just happened? Okay, 2, right? Now, let's also look at like what happens when it's more than like, and it's not only n plus 1, but more than that. So what happens if it's like B 1 and 3? Again, the same rule should apply because there is no subset of size 3, and the maximum number of dichotomies that I can have on one point is 2, right? So this will go on. So that made our life like really easy, right? And here again, when n is 2, and I'll start here essentially, right? N plus 1, it is going to be 2 to the n, which is under 3 and 4, right? And this 4 should go on, right? Because the same logic applies. And again, here it's going to be 8, and then 8 should go on because again, the same logic applies. And then this is going to be 16, isn't it? And then 16, and then this is going to be 32, and that's it, right? I cannot come up with something here because it's 6 and 6. And now we should actually start thinking about n and n because that's what my diagonal values are going to be. Okay, so let me just get rid of this part because I want to stay on this page as we are filling up the table. So I don't want to just distract us from what we are looking at right now. Okay, so let's look at Bn of n. What does that mean? Okay, so the maximum number of dichotomies given n such that no subset of size n is shattered. Well, I'll give you a very simple example. Let's say I have like 2 points, right? And what I'm saying is like B2 of 2 essentially, right? Just to illustrate the point that I'm trying to make. Okay, all the possible dichotomies are essentially 2 squared, right? 2 to the 4. But if I have all the dichotomies listed here, let me just list them so that it makes our life easier. And sorry, this one is going to be this and then this, right? So here I'm saying come up with the maximum number of dichotomies such that there are n points and no n points are shattered. Well, this is kind of violating the definition of Bn of n because it is shattering all the points, right? One way of getting out of this is to just like discard one of these, any one of these, just discard them, right? So basically I'll be left with these 3, which is nothing but 2 squared minus 1. Similarly, if I had like 3 points, I could come up with 2 to the 3, which is 8, and then just like discard any one of them so that I don't shatter all those 3 points. So basically Bn of n should be equal to 2 to the n minus 1, right? So all these diagonal elements can now be filled. Now I know that this is going to be 4 minus 1, which is 3, and then this is going to be 9 minus 1, which is 8 minus 1, sorry, not 9, 7. And then here it should be 15, most likely. 15, yeah. And then this, I hope I'm filling the right column. This has to be 31, right? And then this should be 63, just by following this formula. Okay, so now basically we have filled up half of this column, but like half of it remains, right? So let's try to find out further how to find the rest half that remains, and then also come up with a generic value for this Bn of n. I think I'll just take a break here and then begin in the next video because this might get like too overwhelming. So let's just stop here because we filled half of the table and then see you in the next video.